So, you know, there's the leading edge, and then there's the bleeding edge, and then there's you running ahead of the blade, right? And a lot of times I feel like what we've been doing the last few years is running ahead of the blade. I chose this title with all the weird mixed metaphors here. I don't know if I even want to say tongue-in-cheek, but because, for one, I have a daughter who's now 29 years old, and when I first started going to UPSLA in 86 and the years after, she was always fascinated that I went to a conference for clumsy people. And so I said I had to do some sort of play on the words, just for fun. But what I'm going to talk about here is our experiences with a project inside of IBM Research called Renaissance. And I'm going to, in true rapid prototyping and agile style, I've reshuffled all of my decks since yesterday. So it's I'm going to also talk a little bit about, give you a little bit of a picture about what's happening in the very, very big picture of massive parallelism in computing globally, which is also what I work on at IBM, and of course what IBM is very interested in for all kinds of reasons. Unfortunately, very little of that has anything to do with Smalltalk, but it's very interesting from a technology perspective. So, coming soon to a computer near you, massive parallelism, and it's a really, really, really different world. We were really surprised when we started working with manycore chips. You know, everybody's got multi-cores in their laptops and stuff now, but manycore is a different world. It's not just more cores. It's, you know, we worked on a Tylera 64. I'll talk a little bit about that at some point. It has 64, it was like having 64 PDP-11s. Really fast PDP-11s, but still, you know, it's like that. It's not like having 64 Xeons sitting there. It's a very different world. You have a lot of issues. You can, one core can talk to another core in 2 cycles, but getting anything off the chip, because you don't have any more pins, you got 64 cores with the same number of pins. So you got all kinds of issues, lots of technical challenges with multi-core and many-core. So this is kind of what's been going on. This is kind of the transition we've been underway. You know, forever we were working with basically single core, single threaded systems. It's 100% serial programming. We could do fake parallel stuff with threads and processes and various things. But, you know, really it was fairly straightforward. Programming was a joy, and we just kind of let Moore's Law keep turning the crank up, and things kept getting faster, everything was great. Then we kind of hit to where we are today, where we have multi-core systems that are pretty predominant. You know, you're in the tens of threads. It's starting to get complex. It's starting to be a little hard. You know, if you're really trying to get performance out of your system, maybe you're doing 20% parallel programming in the middle of all that. In the future, this is the situation we have. 32 to hundreds to thousands of cores. We started talking about 1,000-core systems about 4 years ago. I'm started seeing other people talking about it now as feasibility. And we're not talking GPUs here. We're talking like, you know, regular kind of RISC cores. The problem is at that many cores, the threading model breaks. Complexity exceeds our programmer's ability to deal with it. So we're going to have a really, really different world. We're going to need the new architectures are going to require new programming models, new languages, new operating systems. There's all kinds of stuff that's going to be very different in this space. You already see that because in the last couple of years, what have you heard? Lots of new programming languages, right? Like Dart, for instance, or Erlang, or, you know, all the different things people have been playing with out there now. Everyone's trying to figure out, how do we deal with this new world? But nobody's really got the answer. We don't either. You know, it's an open question right now, a very exciting time in computer science research. Now I'm going to shift gears a little bit and share with you a couple of thoughts out of some of IBM's thinking on where global technology is going. So this is kind of this is the model we've been on for a long, long time. This compute-centric, CPU-centric model. The CPU was the most precious thing, the most precious commodity in your system. You wanted to make sure it was humming all the time doing useful work. But, you know, it was limited to how much it could do. So what you did is you had this deep memory hierarchy, and you spent all your time managing, staging all the data so it could get to the CPU, and then staging all the data out of it so you didn't block the CPU, right? And that's what we've been building forever. That's basically been computing. Now there's some really interesting things changing out there. We've got storage class memory that's coming on board, lots and lots of persistent memory. You see it now with flash. You're going to have phase change in a couple of years in quantity. You've got many-core chips, you've got FPGAs, you've got massive parallelism coming, and of course GPUs. And what's really going to happen here is an inversion of that model. So instead of it being CPU-centric, where all we're talking about is feeding the CPU, it's going to become data-centric, where you're going to end up with huge masses of data, which, by the way, and huge, I'm talking, like petabytes. Huge masses of data that are too big to shift from disk across the network to your CPUs and back. It's just too big. It just takes too long. It's prohibitive. So all of a sudden you start talking about these systems that are big clouds of data with processors sprinkled all around through them. And what's the key there? The key, and we'll talk about it a little bit here on the next chart, is the key there is latency. Latency is becoming the driver. Latency and power. I'm not going to talk so much about power, but power is an obvious one here. There's only so many nuclear power plants in the world and hydroelectric dams, so we can only build so many of these big systems until we figure out a better solution. This is a trend chart, and people who've looked at hard disks forever, and people go, wow, hard disk prices just keep dropping and dropping and dropping, and they're always going to be cheaper than any kind of memory-based solution. That's true, but if you look at the curves that are happening here, let's see if I can figure out which one is the, there it is. Okay, so there's the hard disk curve, and we're now well below $1 a gigabyte now. You can go down to your local office store and buy terabyte hard drives. It's just boggling. But if you look at what happens with DRAM, DRAM is still trailing way behind that. But if you look at storage class memory, in this case this is phase change memory, what you see is it's starting to get down to this interesting point. And if you project this out to 2015, you end up in a situation where you have about a nickel per gigabyte. That's about 50K a petabyte. That's a little too much for you and me to have a petabyte of RAM, but it's not too much for, say, an enterprise class server to have. So you're really starting to get in a different space. But the key here is this latency number. So if you look at RAM, Flash is wonderful. Flash is a whole lot, it's a whole lot better. It's 100 times faster than hard drives, but it's 100 times slower than storage class memory. For instance, like phase change. So what you're going to see is a real dramatic change in our whole way of thinking about storage. When you start getting to this space where you have all this storage class memory, do you treat it like really fast file system, or do you treat it like memory? Your architecture changes dramatically when you start thinking that way. And we're going to have to start, the old file models are not going to make any sense in this space. So lots of interesting changes there. One other one I'm going to do on this view. Now this is looking at system capacity or capability versus system density, which is kind of the inverse of latency. You can kind of think of it that way on systems. So right here is where we've been for a long, long time. We were doing scale down. That was your classic, features get smaller and smaller, your classic kind of Moore's law curve. We're getting close to the edge of that now, right? You can't get it much smaller, at least with current technology. If Kurzweil's right, we'll figure out something else, we'll go another level, but I really doubt it for a while. So we're kind of reaching physical barriers for how far we can scale down a device. We've also reached physical barriers with how far we can scale up a single device, like a single chip. I don't know why my phone's ringing. Let me turn that off. There we go. So now you end up with, we got these great big chips, but the problem we have there is what? One, we still only have so many pins. Got a problem there. The other problem is the chip is so big that the speed of light now starts mattering. Is you can't get a signal from one end of the chip to the other in the cycle time that you want to do it in, right? So we're just hitting hard physical barriers. So we fixed that problem with various kinds of cloud computing like Google and other people have done by doing scale out, right? So we just lots and lots and lots of nodes, lash them all together with a bunch of Ethernet cable, and we can just scale forever. As long as your algorithms don't require crosstalk between the nodes. If your algorithms require you to slosh data around, what becomes the bottleneck? That 1 gig or 10 gig Ethernet cable, right? So then you have to start saying, where are we going to go with that? Well, what's happening now and what's going to be happening for the near future is what we can talk about as scale in. And the idea here is more and more and more density. More memory, more processing in a tight package to keep latency low. Now all these things sound like I'm just way off in the space. What does it have to do with Smalltalk? What does it have to do with objects? Okay, I'll get there. The next thing I want to talk about is approximate computing. So there's big implications of this new kind of architecture that starts making us think that we've got to rethink fundamental things about programming. So here's the bad news. So here's your classic balance between memory, instruction level parallelism, frequency and power, and they're all kind of interrelated to each other. And the problem is we started hitting the walls. We've hit the memory wall, we've hit the thermal wall, we can't heat these things up anymore, they melt. We've hit the power wall, we can't pump more power into them. We can't get them any faster. Instruction level parallelism flattened out. We got a problem. The thing is all these things are happening more or less at once, and what it means is the future application performance is going to have to come from somewhere else besides hardware magically giving it to you, which means the software's got to think about it. Now, we forever have said we want a nice programming model where people can think in this wonderful world like Smalltalk and objects, right? Big single image, all your objects live and breathe, they're all live. You don't have to worry about what's under behind that curtain. That's going to have to change. So how do we deal with this? So one of the things we do is we go from single cores to many cores. We're working on that. Now, the single core complexity is matched out, the coherency cost is matched out, the development cost is maxing out. We get more transistors, Moore's law is still good for a few more cranks. So we go to many-core, multi-core, and many-core architectures. We get smaller cores, that's great. This gives us a vast amount of new, massive parallel computing, but at a cost. Soft errors. These things get smaller, guess what? They don't all run real well all the time. They have all kinds of cosmic rays become your enemy. I mean, it starts getting serious. So this has some other implications. So future software has to not only exploit the parallelism, but it has to tolerate the errors and the coherence issues that we talked about as well because of the communication overhead problems. So at the same time, we're getting massive amounts of new data. You've all heard about the big data, the exaflood, and all these kinds of things, and analytics and all this kind of stuff we're doing. It's all unstructured. We've got less time to do it in. We need more cycles. That's great. But we can't move the data around fast enough. And I talked about that already. So what do? This is the thing I wanted to talk about before we get into the Smalltalk side, because this is what's informing our thinking and our research. So traditionally, our default assumptions has been maximum accuracy, maximum precision, maximum completeness, and the hardware would just make it all faster every few years, right? So, all these different things were things that we maxed out all the time in our thinking about programming. Now, if we dial back those assumptions within limits, within reasonable limits, we can get tremendous gains in performance and better exploit parallelism without more frequency scaling. But what does that mean? That means you start backing off of some of your assumptions you've held forever. How many of you believe that floating point calculations are actually precise? Right? They're not. This is your bugaboo. But we treat them as if they are, unless of course you're down in some numerical thing where you really find the problems. We have this all the time in the work that we do now. So what we're telling you, this is kind of a broad general thought in IBM Research right now, is we have to move to a notion of approximate computing where we stop thinking about everything being precise. Guess what? The world isn't either. So we're actually getting closer to a modeling of the world. I've mentioned a little of this. Coherence is less important. Failures have to be, at fine grains, have to be tolerated. You can have reordering of operations. There's lots of interesting things that happen when you go to this kind of approximate view. Calculations may never finish, and the bottom there is really important. Non-determinism, which has been our absolute mortal enemy forever, starts becoming a friend. So the idea is how do we ride that? How do we work it that way? So our research challenge in this project was to figure out a new general programming model for massively parallel, low latency systems, which are the things I'm talking about here. That's easy to understand, easy to think about, easy to program, scalable, performant, and a programming model for bridging all this massive data flow with the massive data storage, all the things going on. So we started the Renaissance project, David Ungar and I did back in 2008. Our goal was really twofold. We wanted to find a breakthrough in programmability and performance at the same time, because oftentimes you can do one or the other, but we tried to do both. We were given the freedom to take a clean slate approach. We could do anything we wanted. We could try anything out we wanted. And we looked at some challenging applications, which we'll talk about in a minute. And we started out with the thought of, say, we're going to build a 1,000-core test bed. Now, at the time, the only thing that we could really use here was something called the Tylera R64 many-core processor. It's got 64 RISC-based processors in it. And we were prepared to build we found out that the hardware wasn't available to lash all those PCI cards together with the latency we wanted. But this was our goal originally. So we selected a test bed, like I said, the Tylera 64 chip. It's got about 64K of cache per core. That's its L2 cache, and you could share the L2s across it. And we were going to rewrite the Squeak virtual machine to run on Tylera, and eventually we ported it to Intel CPUs as well. Now, I'm not a VM guy, so I'm just going to bring this one slide up about the VM, but we had some really interesting architectural evolutions as we went from that. We started from a simple single interpreter, single heap kind of world. We started splitting these up across the cores, and what we ended up with all the way down here was that every core ran the interpreter, and it had a read-write heap and a read-mostly heap. And so what we ended up doing was dividing the work up in this massively parallel fashion, and we built all kinds of monitors and various gauges and things to run all this. All this was done in MVC. We started out with a very, very small, the actual development image that we worked with in this world was a 1.7 megabyte Squeak image. We did that because we could run the whole thing in cache. And again, getting off the pins on these things onto DRAM is a real problem. So that's what we worked with. So we picked a platform, we defined a language, which this is kind of an overview, I'll talk about it in more detail later. The language that we defined was called Ly, L-Y, which comes from the common suffix for adverbs. And it was a JavaScript-like language. We built an IDE for it so we could inhabit it and live in it, all kinds of tools and different things. And we tried some applications. So what we're seeing right here is, this is Craig Reynolds' Boyd's algorithm. So you basically have flocking going on. And you're seeing here we've got number of running processes is running around 50, something like that. That's running processes. Here's all the cores. So here's 56 of the 64 cores, which we could access from Smalltalk. The other 8 were running Linux. And here's what was going on with it. You see the bytecodes and where the processes are running. And here's the memory usage. You can see how various areas get hot. That central core where all the hotspot is, that's the one that's running the UI. So you can actually watch these later as you see. You can see where garbage collections happen, things like that. Then we went to, for as far as experimentation goes, we built the Roar VM. We built Ly, which was the JavaScripty one. It was really too slow, so we built something called Sly, which was Ly and Smalltalk, which was a lot faster. And we started experimenting with some new language ideas we'll talk about in a minute, ensembles, adverbs, and gerunds. We're currently we have a C++ version of a non-deterministic system that we're also experimenting with in doing in-memory cubing, as in things like Cognos TM1 hypercubing analysis. And I've already said that. I did want to mention our collaborators. IBM has this really nice open collaborative research program where we can engage with universities, and the agreement basically is all the results are going to be open sourced. So we're working with Andrew Black at Portland State and some of his students like Nathan Nifong and Max Orhai, Theo de Hant in the Free University of Brussels, Stefan Marr, who was just now finishing his PhD under Theo's supervision, was basically our other VM guy besides Dave Ungar, and he's the one that's launched the Roar VM and manages the open source activity of that. And I mentioned that we have open source the virtual machine. That's it, Roar VM. Just Google it. You'll find demos and papers and all kinds of stuff, and a number of papers that we've talked about different things. Now, so when we looked at this problem, we said we're going to look at for an application that we can take advantage of massive parallelism. Well, one of those obvious applications was physics. It was physics simulation. So we started out looking at game physics engines, and we found that, yes, you could do massive parallelism, but if you're going to do the key to performance, and in fact, if you look at game physics engines, it's all about tricks. The general physics model is the simplest part of it. Where they get all the performance is, okay, something's happening on this side of the mountain, and you're over here so you don't see it. So guess what? We're not going to render it. We're going to skip through things. We're not tracking every bullet that's flying on the other side of the mountain, right? It's all about tricks. And what you found was these dynamic neighborhood interactions were the most important. That's the key to performance. Now, we started looking at a simplified physics model, which was the bird flocking behavior, Craig Reynolds' Boyd's algorithm, and we found the same kind of dynamic neighborhood problem. So to do the Boyd's computation, every simulated bird is trying to stay within its little group of flock mates, and that's what makes flocking work. And so it's all kind of local physics interactions, even though there's a large number of things going on. Then we went one level lower, and we looked at a parallel version of the game of life, where we were also looking at dynamic neighborhood management. So one of the keys to this in our thoughts was we're going to have to be able to have these kind of dynamic, fuzzy neighborhoods of interacting objects that are going to change all the time. That's going to be a key element to some of our thinking. So a little piece on the approach that we took. So first of all, we're focused on harnessing emergence. So biological systems have done massive parallelism forever, right? So can we have a programming model achieve similar success by mimicking this? So in emergence in general, these are the keys for managing emergence. If you're going to try to harness emergent systems, you need scale. You need typically lots of numbers or lots of time. You need scale in that space. Lots of positive and negative feedback. The more the better. Stigmergy, which is indirect communication in things like ants and termites. It's actually the little pheromones that they leave around on things. You can use that technique in all kinds of fascinating ways in computing. Some inherent randomness to keep things from locking up and give it some adaptability. And then this other weird thing called apoptosis, which is something that comes from the cellular biology world, where cells in your body, if they start getting out of whack, they just pop. They kill themselves, they suicide. And so when you take all those thoughts together and you say, how is that going to work for harnessing emergence in many-core systems, you're going to have large numbers of cores or threads, lots of dynamic data sets. Y'all have all heard of the curse of dimensionality, right? Once things get up to about past 3 dimensions, things start getting really nasty. There's a really, really bright guy named Pinti-Kernirva. I'm probably saying his name wrong, but he has an alternate version of this. He says there may be a curse of dimensionality when it's at 2 or 3, but when it's in the thousands, it's truly a blessing. And go look him up and read his stuff. It's really amazing what he's talking about. But it's all in this approximate computing kind of space. Apoptosis, like I said, you want your objects or your threads or whatever to suicide when they escape operational norms, because guess what? If you got millions of these things, what if you had 1 million threads? Are you going to be able to go debug each one of them? No. They've got to take care of themselves. This becomes important. Positive and negative feedback. Well, when we talked about latency in the system, when you think about, say, having a big Smalltalk image and lots of objects and threads around, but it's spread all over a whole bunch of cores and maybe on a whole bunch of nodes in a distributed system, how are you going to keep from thrashing yourself to death? Especially as the object relationships are changing all the time, right? So what you have to do is you put in feedback loops where you say that the objects attract to where they're being worked on, or the threads move to where the objects are, and vice versa. So you get this kind of dynamic flocking behavior of objects and threads over the latency landscape of the massive parallel system. That's the kind of thinking that you have to think about in this space. So embracing non-determinism was one of our other key things. So why do that? Well, first of all, when you get in massive parallelism, you have a state space explosion. You literally don't have enough slots in your head to manage the state space. You will not be able to think it through. So you're stuck. What are you going to do? You can't afford to worry about order of execution, and global synchronization is going to be impossibly expensive. Again, that's one of those things we've always assumed. We're going to have synchronization, locking, transactions, all that stuff. It also matches the hardware trend. So if you think about one of the things that's happening in these many-core systems is they're not powering everything all the time, right? So they're constantly trying to save power. They're shutting down cores everywhere and firing them back up, whether that's in your GPU or your CPU or your multi-core pad. And so what's happening is you're virtually changing the hardware configuration underneath the operating system and the application all the time. So in traditional ways, we thought, okay, I've got an operating system with a bunch of assumptions about how things work. I've got an ISA under that my compiler writes to, and I've got this nice chip that's going to run my ISA. In hybrid computing and heterogeneous many-core systems, you basically you could have a different hardware configuration almost every cycle running underneath your application or your virtual machine. So you have to take that into consideration too. And I already mentioned about soft errors. By the way, that means that singleton operations, if soft errors increase across this thing, writing a function that's going to execute only in one place and you're trusting that that one doesn't fail starts to get more and more and more risky. So you start needing to think about ensembling techniques, which we actually use the term later in a different way. So embracing non-determinism as well. So forever we've said A plus B plus whatever equals C. We've got to start thinking in terms of approaches C. where it gets close and it's good enough. That's the point. Is it good enough soon enough, as opposed to absolutely right but way too late or way too expensive? And actually what you end up with, if you take non-determinism and you get, again, these large numbers of processes or threads or whatever, you kind of get almost determinism. So it's actually not that bad. Let's see, I've already talked about that. Okay, here's some of the principles coming out of this non-determinism thing. No single member of, say, a bird flock or a flock of processes is more important than the group. The members act only indirectly with the group via just their local neighbors. There's no global knowledge because you can't synchronize. They have similar kinds of behavior, which implies a kind of polymorphism. They can come and go dynamically, but the group stays the same. There's kind of a group state that's persistent, even though the local states are all over the place. And so what are we going to do with this, all these thoughts? This is what we did. We went and noodled on this problem for quite a while. So we decided to try something. We created a programming thought called an ensemble, and we looked at it and we said, okay, we're going to go replace collections and iterations with this new idea, this new kind of parallel idea. So all parallel activity revolves around either collections of data or collections of tasks, right? So you have a data parallel thing, like everybody's in the room, we're going to all eat the pizza, we all grab a piece of pizza and we eat it, right? You have task parallel where the goal is to win the race, but you got all the horses that are all running separately and they're all trying to win. Whoever wins first wins, right? That's kind of the two main spaces. Now, loops and collections in programming have been fundamental to the way that we deal with doing lots of things over and over, whether it's parallel or serial. It's also the most common source of programming bugs. So we looked at that and we said, if we're going to start doing that new, then we're going to need some sort of a new language. We call this thing an ensemble. An ensemble is a new kind of object. It's both a singleton and a collection at the same time. Now that's not actually new with us. Kent Beck did this when he was working at MassPar. Actually, Ward Cunningham did it years and years ago. He gave every object collect, select, and do behavior. And of course, it just defaults to doing it for itself. And then Kent did some interesting things at MassPar with parallelism where he exploited some of that. It's a very interesting idea. You say, so now an ensemble can have some number of members. They can be objects or other ensembles. And the membership's dynamic. And you can't, as a programmer, know, and you shouldn't care, how many or who is in the ensemble. Just like with a bird flock. You don't care about every particular bird, right? All you care is that the flock keeps doing what it's doing. So regular messages sent to an ensemble are broadcast to the membership in parallel. The results are collected. They can be aggregated and returned. And this is quite a radical departure when you think about getting rid of collections and iterators. Lots of different examples of ensembles in the world. It's a natural way of thinking about space, the solution space. Couple of examples here. So here's like if you're modeling a flock and here's your boids, you'd have an array or a collection or something and you'd use iterators to process it. With ensemble orientation, you just have an ensemble, you put them all in there and there's no notion of order, there's no notion of anything else, and you don't do iteration or enumeration, you just throw a message at it and it does it automatically. I've already talked about that. Here's another example. Now, so here we have a parent object, some child objects, and we have an array of children. In ensemble orientation, you just have an ensemble of children where you wouldn't have that intermediate thing. Now, granted, the implementation might well have a collection down underneath it, right? In fact, we did when we implemented it. But the point is you don't think of it that way anymore. It's not accessible to you. So the implications, if we did this, collections cease to exist as a kind of object. Now, that'll make a shiver go down your spine. Collections are one of our most powerful tools. But every object then becomes an ensemble of one. Enumeration and iteration becomes a native behavior. I'll talk about adverbs in a minute. And single, precise, unidimensional values become a degenerate case. Maybe one that we use a lot now. But remember that whole non-deterministic kind of clouds of things. You can think about doing math this way. When we do it, it's called probability, right? So you can think about a lot of what you do in probabilistic systems as being the way you normally would do math, for instance, as opposed to how we typically do it. Here's another example about precision and fuzzy. So here's a rectangle object with a couple of points. Here's an ensemble orientation of that, which would say the origin is some number of points and the corner is some number of points. So you could think about having this kind of aggregate always going on and dynamically changing all the time. And if you wanted to do a calculation on it, you would have to do some sort of reduction across that, or you'd pass the whole collection of points along and they'd continue to do it. So instead of thinking like a single point, you start thinking about a cloud of points that represent what's going on. Lots of interesting things. I was already thinking about what you could do with a GUI layout system with something like this. So let's see, I've already talked about that. One interesting problem is what do you do about inheritance? I'm not going to talk about this much, but just to mention it, since we're sending messages to things, and inheritance was about who understands what messages, it's about inheritance of structure too, but one of the things is about, what messages do you understand? Do ensembles inherit from other ensembles? Do the objects in it may inherit from different trees? You get all kinds of interesting things with inheritance. Now I'm going to talk about what the implication of, if you go to this ensemble thing, you end up with having some new opportunities. We talked about something called adverbs and gerunds, and they formalize and exploit execution strategies. I've got to describe all of this. So if you look at ensemble computation, it varies from dependent and serial all the way to independent and parallel. There's sometimes things that you just got to do serially. And when you get the results back, you might want an ensemble of the results. That may be important. Or you may need them reduced to a single object. And this is a continuum. There's all kinds of possibilities in here. So we decided to separate the how from the what and the who. And so instead of having just subjects and verbs like we do in normal declarative kind of programming and object-oriented stuff, imperative programming, we have subject and verbs like normal. Who do you want to do the work and what do you want him to do? And then you have adverbs. Adverbs tell you when, how, right? There's all kinds of things. We went and looked at a very long list of adverbs just from the dictionary, and I was surprised probably 80% of them had natural application to programming. When you started thinking in this way, you should like, wow, if I had that as an element in my programming language, it would be very powerful. And then gerunds we'll talk about a little bit too. So the way adverbs work is adverbs mediate, you send a message with the selector, the arguments, and the adverb. The adverb mediates how the messages get sent to the contents. And there's all kinds of possibilities here, but you could say serially, concurrently, or some typical ones. You could say eventually, immediately, occasionally, silently, loudly, right? All those things. Now, what you already, as programmers, know the code I'm talking about, because we do this all the time. But that stuff is glue code. That's the stuff that never gets formalized in all of our programming. What adverbs allow you to do, in gerunds too, is formalize what used to just be glue code. And now they become language elements and things that you can write and reuse and share. And so it's really pretty neat idea. Gerunds, on the other hand, handled the results. So you'll see it's sort of like the reduce phase in MapReduce, which is a subset of what we're doing. Here's a little more discussion. So, for instance, which members of the ensemble will respond to the message being sent? That's one of the things. You might say, I only want, you can think about an ensemble as a resource pool, for instance. That's another way of using it. So you don't want everybody to take every message and work on it. You just want whoever's there to take a message and work on it. You may want it to be generate them. So you may start out with an empty ensemble, but knows how to generate its members as needed. So you could think about kind of a dynamic growing pool and shrinking pool of objects that are serving those requests. How the arguments are going to be handled. So if you send a message with arguments, what do you want to do? If I just forward that whole message and arguments to every member, that might be what you want. Or you might want to map the arguments with the message to each member. Right? There's all kinds of interesting possibilities. You might want to have it loop round robin through the collections to handle them. Lots of different things. Then there's execution strategies, which, remember I talked about we're going to have to, the underlying hardware configuration at any point in time is going to somehow have to find its way up the stack to get efficiency. These execution strategies, and one of the really key things about ensembles, is ensembles give you a way of expressing intent of your algorithm that used to get lost in glue code. Now you can express enough intent that if you have these standard adverbs that you're using, then your virtual machine can say, oh, he's really trying to do this pattern. And so I know what my hardware is right now, and I know what pattern he's really trying to do, so I can map the two together more intelligently and get better performance. And so it's about a way of exposing that. And then you have the results when they come back. You might, like for instance, some of the gerunds that we use, like totaling. I want all the answers totaled when they come back, or averaging. Or, for instance, caching. I want you to remember these answers. Don't, cache them locally in the ensemble. So if I ask the same question again, you give it back. It's like memoization, right? So there's lots and lots of ways you can use this idea. So the programming model, when we looked at language design, we wanted to hide the complexity and streamline what we want people to think about. And I've talked about these already. I did want to mention, though, that adverbs and gerunds and ensembles, map-reduce kinds of strategies are a tiny, tiny subset of what this thing covers. So it's a generalization over all the things we've learned about map-reduce kinds of approaches. Oh, I'm not even going to talk about that. Probably good for your eyes. Okay. One of the things I did want to mention is this is a very natural progression in programming, is to take usage patterns that become idioms and then they turn into language elements, right? So here's a standard one. We used to start out with what? In assembly, branch not zero, right? That was your branching instruction. Then we had ifs and go-tos, right? Which, guess what they do underneath? Branch not zero, probably. Then we had do's. Used to, you didn't have any do loops, and you had to do everything with your own counting and iteration and branching. And then we went to, collection iterations. And these things, so when you start thinking about how many idioms do we have in our programming, and we have design patterns that cover a lot of these things, but I'm talking about kind of the smallish patterns, the smallish idioms, then this allows us a way to capture those, formalize them, share them, teach them, all those things. And I'm going to skip through that. Talked about that. Too much detail. Remember I said ensembles could be thought of as a whole or as a group all the time. So you need to have this way of talking to it as a whole as well. And it's kind of reflective in a way when you kind of think about it. It's like I'm talking to the group, or I can talk to the group thing itself. And so we had in our syntax, we used a dot. You're not the only one, Google, that uses dot. We used it as a reflective send. So if you wanted to talk directly to the ensemble, you could use a dot to send a message instead of a dot. So here's kind of what the syntax looked like at the end. You have the receiver, you have the message, you have the arguments, and then in the Lee, which is a JavaScript-like version, we had a dash, and then you could put the adverb expression in with the arguments. You could compose these things. The adverbs can have arguments themselves. For instance, if I wanted to do something variably and I wanted to give it, what was the variation, what was the probability I wanted it to vary by, I want to send 1% in or something like that. The arguments can have adverbs themselves. I'm not going to try to explain that one. So here's the Boyd's algorithm written in Lee. So it's mostly JavaScript, doesn't look very differently. But here you see something interesting. So you have the class Boyd, and it sent the message inflate. Now inflate says, give me back an ensemble of these. So it's going to create a bunch of instances and hand you back an ensemble. In this case, we said we want 1,000, and we want you to do it fuzzily. So fuzzily was an adverb we wrote that said, go and vary all the parameters. Each instance is going to, all their parameters are going to be varied within some bound. And so what I ended up with is basically a random distribution of 1,000 Boyds, right, with all their locations randomized and their headings randomized and their velocities randomized. Here you see us using it in one case. We're trying to find the centroid of the flock, so we send the message position to the flock, and then this is before we use gerunds, or we would have said averaging here. And we're averaging the result that comes back. Let's see, where's another one? Here's one. So this is a select case. So what I'm doing is this is choosing where, let's see, what is it? This is computing the neighbors of a Boyd, and he's saying, hey flock, who's near me, basically, selectively. And what he's doing is he's going to hand back just the members that answered true to the question, basically. So it's basically like a select over an ordered collection. And there's a few others, but I'm not going to talk about it. So that's kind of the example. Now, I want to just leave this in here for a second, because the things that make parallel computing hard are these things, right? It's basically synchronization. Synchronization becomes your enemy in this space. I may, if I have a little time, talk about how we're dealing with that, but basically we're dealing with it by ignoring it. Not completely ignoring it, but we build systems intentionally that can have race conditions, that can get way out of sync with each other. You know, we used to do this, it's called garbage collection. You know, we used to have to manage all of our memory by ourselves, right? And if some little thing got wrong, the whole system would crash, and we built garbage collectors to take care of it for us. What was the price we paid for a garbage collector? Not knowing the physical memory address anymore, right? You can't use it, you can't trust it, because the garbage collector is going to shift it out from under you. So now you think about this from a standpoint of, we started talking about consistency correctors in the same sense as garbage collectors. So you let your system get out of sync, and you have these processes that run around, much like garbage collectors did for memory, and what they do is they find the inconsistencies and they fix them at some rate, right? And so you're creating inconsistency, but you're handling it at some rate, and you can build systems like that. So inhabiting the model, did I hit the other button? Yeah. So like I said, we built a bunch of stuff. There's our, well, all the different goodies in the laboratory. All this is in the open source environment. It's all in MVC because we couldn't afford to run Morphic in this environment because it was too memory impoverished. By the way, that's a really interesting question, massively parallelism. How in the world are you going to have a massively parallel driven user interface? I'm not talking about GPUs and pixels here. Okay? Think about Morphic, for instance, where you've got lots of, you know, your UI entities basically act as if they have their own little, you know, processes running. With one real problem. Somewhere or another, they've got to do a bit blit to the screen buffer, right? Guess what? That's got to be serialized. How are you going to do that? How are you going to build a really high performance, massively parallel user interface paradigm in this kind of way? We don't know. But it's a really nice problem to think about. We originally tried to do this actually just in Smalltalk with standard Smalltalk syntax. This is the first version of it, and it was so ugly we couldn't stand it. That's why we decided we're going to have to write our own language to try it. We do have our collaborators at Portland State, Andrew Black and company, have a really nice proposal for a very nice Smalltalky kind of syntax now for this that may get adopted. We built all kinds of interesting tools. Again, very, very ugly syntax around it. This becomes a real interesting problem. I didn't have any charts on this, but I wanted to mention it. One of the barriers that we hit, you think about what we're doing with adverbs and gerunds. So you had your normal kind of message sending, so all the stuff you'd normally do in Smalltalk, for instance. And then for any message send, you might want to add adverbs and gerunds and maybe their parameters. Now what's that going to do to your code complexity from a visual standpoint? It's going to go crazy, right? So you may want to be able to like fold and unfold those things or see that they're there and not see them sometimes or stretch them or whatever. And what we realized was that we are stuck complexity-wise in a one-dimensional space in programming. I'm not talking about visual programming here, okay? I'm talking about two-dimensional programming or three-dimensional programming in that right now all we have is one long character string. Yeah, we have editors that wrap it around, right? But it's just one long character string. It's one-dimensional. When you start talking about functional metadata, which is kind of what adverbs and gerunds are, they're metadata on each function, you really have another dimension that you need to be describing things in. There's no kind of editing paradigm out there that we found that matches this thing. So lots and lots of interesting questions and problems there. We built an environment, we've seen this part. Okay, lessons learned. It was too slow. When you're running an interpreter on a virtual machine on a impoverished core, it was really, really, really slow. So we went to what we called SLY, which was Leon Smalltalk. It's a lot faster. There's an example of 50 parallel boids running on 50 Tylera cores, and that's about 100 times faster than it was on Lee. Then we decided we needed some more speed because now we kind of got the ideas down, and now it's a matter of how fast can we iterate, how fast can we test out new algorithms. So we moved from the Tylera to a Mac Pro with 8 cores and 16 hyperthreads, or 4 cores and 16 hyperthreads, I guess it was. And Stefan Marr at the Free University of Brussels did that port for us, and that's also out there. So there's all the platforms that we have currently supported on that. And I'm going to summarize here. So one of the things we realized up front when we started looking at this is somebody had already figured out this problem a long, long time ago. is a language called APL, right? APL has lots of interesting lessons to learn from. Now, granted, it did it primarily for numbers, and you could also do it for text, right? So, extending that to objects or, ensembles or other kinds of things is more work to do. There have been follow-ons to APL which did do stuff with objects, so it's interesting to go look at. But unifying the many in one kind of thing, where, vector or scalar operations were kind of interchangeable, you didn't care about it, that's part of that thought process. Then when you go look through the languages, what Lisp brought us, what Smalltalk brought us, what Self brought us, and of course, JavaScript is an ancestor of Self. In fact, you noticed all the Selfisms in Dart, if you haven't yet. That shouldn't be a surprise given some of the people working on it, but that's a good thing, I think. So here's where we're headed. We're looking at where do we go beyond collections? Where do we go beyond collections? And how do we formalize the programming idioms that are lost in glue code that can inform massive parallel performance on a dynamically changing substrate of hardware with no common ISA, and all the kind of things we used to trust are gone. And then how do we embrace this imprecision and non-determinism? What this all means is a real sea change for algorithms. When we started thinking this way, we started thinking about even just simple things like a sorting algorithm. You start thinking really, really, really differently. And I think we're really, whether this is the answer or not, I think we're really starting a whole new dimension in programming and computer science in this new space. So it's very exciting. I love being able to have a massively parallel Smalltalk to play with, which I get to do anyway when I'm not working on this. But that's basically my talk. So questions, comments, thoughts? Yes, over here. We'll get the mic to you.
You sort of present this as though it's an all or nothing inevitable conclusion, and I don't really get that. I see this as sort of an add-on tool to the existing environment. I use a supercomputer cluster when I need it for a certain problem space, and I use a conventional machine when I need it in a certain problem space. I assume you see that coexistence at some point down the road.
Oh, sure. Well, I mean, there's still an awful lot of things that one processor is just fine for.
Yeah. Okay.
Right? It's like balancing your checkbook, right? You don't have to have massively parallel computer to balance your checkbook.
Right. So the question of how to do graphics or blipletting or stuff, I don't really get why you were presenting that as a.
Well, it's more of a problem of how do you pipeline all of that, because at some point you end up blocking everybody, right? This is the whole problem with serialization and synchronization. And when you start getting lots and lots of that, and even if you take things like isolates and things like in Dart and Erlang, they're sending messages, guess what? They can still have race conditions, they can still, all those things don't go away, right? The locking, deadlocks, live locks, all that kind of stuff can still happen. And so the question is how do you get completely away from that space and then do something that gives you the effect of a serialization, a write barrier or something, but without the synchronization? Yeah.
So I think Croquet is related to this, a model it has, because the idea there is you've got a whole bunch of machines that are all running, you're in this virtual world, but in fact, they're doing bit identical computing. You're actually distributing the computing, everyone's doing the same thing, and the reason for that is so that we can do the 3D rendering I can have a copy of the world on my machine, and then I can render it onto my screen, and then because the data rate between the model and my screen is just immense. And everybody has a slightly different view of it. We're all standing in different places looking at the same stuff, and so we're all going to have a different 3D. Well, the trick then is how do you make sure that all those computers all have the exact same model of the world? And then they do this serialization, and they have tricks where they're making it. Well, imagine that what we're doing is you've got all these multiple processors, and they're all talking to a screen. So now I've got a graphic thing, something that's going to have a graphical representation, and it's rendered onto my machine, but there is a sort of a simple model, and the simple model will change, and then the individual processes have to change that simple model, and you're using some sort of a consistency mechanism to make sure. Though the rendering is all going to happen on my computer, we don't want to try to distribute that. GPUs do a great job of it, and you sort of have to put everything in one place to make that work. And so you figure out, well, what's going to be centralized, what's going to be distributed, and
that's a big part of it.
Yeah.
That's a big part of it. And one thing on your comment in the back. This is a research project that was focused on really trying to find a new way of doing things. So we try to be extreme. But obviously, I mean, one of the things we thought about when we thought about ensembles and adverbs, we said, okay, we're going to get rid of collections, right? Well, one of the things we're thinking about now is what we might end up with is a package that you could have implemented in lots of different languages that give you ensembles and adverbs in addition to everything else that's already there. There's lots of practicalities, right? But when you're trying to make a breakthrough, you don't worry about the practicalities up front. On the whole thing about what you distribute and what you keep to yourself and what you use. One thing I thought of when I was working on this problem was how do you do massively parallel synchronized physics engines with, say, 1,000 users or 1,000,000 user, virtual games, virtual environments. And one thing I realized, there's another trend happening that we don't think about too much, and it has to do with these things, right? And the video pipeline that's being built so everybody can watch two-way video. Now, why don't I have one model, one big physics model running in a cloud somewhere on a big, huge computer with a whole bunch of video? Well, what is that? That's just, well, let's see. I've got my model, I've got a renderer, a GPU on it, and I'm running a video stream. So how many video streams could I produce out of a monster cloud like that and feed to a screen where you don't have to do local rendering anymore? I mean, there's some really interesting things that are changing because of massive parallelism, because of the pipeline, because of the bandwidth things that are happening because of mobile, that really, really challenges our conventional way of thinking about massive parallelism and what we're going to be able to do. So, very exciting time. Other questions? Back in the back.
I'm just trying to wrap my head around the idea of the ensemble. So to me, it seems like it's a mechanism to sort of keep a handle on how much redundancy is in my system, because I need the redundancy to deal with the soft errors and whatnot. So protect myself against these sort of effects. So that seems how a tool to help me with that thing. But I don't see the amount of fuzziness that I sort of felt like you want to convey there, because you still sort of control when the ensemble, how they happens, how big they are. You know, maybe you don't know the details of the elements in it, but you still have a fairly you still have to be fairly specific about how the ensemble comes to be, right?
Right, and you're right. I mean, what you're seeing here are, early, as in 2 or 3 or 4 or 5 people over the last couple of years thinking and coding and building the thing as we're thinking about it. So some of the early things I talked about non-determinism and ensembles and clouds of fuzzy values and all that kind of stuff, we've only done a little bit of work in that part of the ensemble space. We've done a lot more in the kind of collection replacement part of the space. There's a whole lot more to be done there. But yeah, it's early days, and it's very, very strange world. So it's taken us a while to wrap our head around it too. Yeah.
You mentioned both adverbs and gerunds, and some of the adverbs you mentioned were serially, concurrently, quickly, eventually, fuzzily, and averagely. The only gerund I picked up was perceived, and I was wondering if you could name, say, 3 or 4 gerunds.
Well, gerunds are ing words. So,
I guess I got that wrong.
Totaling, averaging, caching, there's lots of things. Really, what we found when we first started thinking this way was we did the ensembles to do the parallelism. We needed to map again. We needed to provide some high-level idea down to the VM of what we intended. We started thinking of adverbs as a way to do that. Then we went and looked at a dictionary. And I know I've said this before. I'm going to say it again, though. Go get a massive list of adverbs or gerunds and just look at them and think of them as, what if that was a keyword in your programming language? What would it mean? What would it imply to you as a programmer if you were picking this function to call? And what we found, we were just stunned at how useful these things are, in our design. And by the way, that's not original with us. Alistair Coburn back in, OOPSLA 88 had a paper that didn't get published, but it was on the committee that year. And it was about using other parts of speech, and that kind of became a little bit a part of some of his methodological work. But using other parts of speech as our programming language, besides just nouns and verbs, is a very rich place that we really haven't explored very well. Other questions? Back here.
When I was listening to you, I had 3 comments which I noted, and I wanted to share all 3 with you.
Okay.
So when we were speaking and turning around the CPU and the memory,
Yeah.
CPU and memory are von Neumann models of computing, which we thought when objects came to place were obsolete. So as object is always memory and CPU at the same time. So having the object glasses on, how do you think, if you abstract away that there is a split between memory and CPU, how would this apply to massive parallelism?
Well, some of the original thoughts about object orientation were you were going to end up with a whole bunch of little machines, right? Each little object is going to be its own little computer. It was one of the really early thoughts. Practically, conceptually, that's an interesting idea, and obviously, we got a lot of power out of object orientation as designers, as humans, thinking about how we're going to, how we think about our systems. From an industry-driven implementation standpoint, it's hard to think about doing. Actually delivering, right? So, what I was showing up there, the first is what IBM's looking at the entire industry of what's happening in computing, right? Like, where's Moore's Law going and everything else. When you start thinking about what objects would do floating on that substrate, what would a virtual machine look like, and what about, single image kinds of worlds, and what about, our objects are so intertangled. If you look at how your objects actually, go trace your objects and what they're actually connected to, they're very intertangled, especially when you get into some of the other classes and globals and things like that. And so you start thinking about how do you untangle that? And there's a lot of discussion going on right now in the communities that are worried about trying to find new parallel programming models about object orientation doesn't seem to fit very well. That's the discussion. Because there's these weird challenges. So, I like it I wish I could make it that way. The hardware's not going that way because we can't get economies of scale building little computers like that. We can't force everyone to take an object-oriented paradigm when they look at their system. But when you look at what's going with the hardware, can we apply the object paradigm as we know and love it? Not without some modification. And I don't exactly know what those modifications are. You had 2 other comments?
Yeah, in preparation of the presentation I will give tomorrow morning, I came across a book called Mycin, written about 30 years ago.
Yeah.
And the basic idea was to take human knowledge, in this case about diagnosis and diseases,
Yep.
and to find the right metaphor to understand how can we express the way a doctor thinks and works to computers.
Right.
And one of the things there was uncertainty. And this, what you were speaking about, reminded me of this concept of uncertainty. And I found it at the end of your presentation very interesting. And also the questions that came up here. You didn't speak about the application domains. Mycin came from a specific application domain. So can you comment on that?
Sure. What you're talking about there, and eMycin, which was actually one of the first expert systems, had a certainty calculus built into it. And
Yes.
if you expressed a rule, I built a version of it in Smalltalk years ago. You could express a rule, and then you could say this assertion with this certainty. It was a floating point number between 0 and 1, if I remember correctly. And
-1 and +1.
a -1 and +1. Anyway, the whole idea of dealing with uncertainty in systems, I mentioned the global technology outlook that IBM does every year. This year they had a whole topic on just that I was involved in too. Don't have any time to go into it. Massive amounts of application spaces out there have all kinds of uncertainty with them. You've got all the sensor-based applications that are happening now. Every single sensor is uncertain. all the unstructured, text analytics, stuff like Watson. You saw, the Jeopardy program. What'd you see? 3 answers, not one, and this amount of certainty attached to it. That kind of processing and computing is what's going to be essential in this massive, data flood that we have right now. Now, how do you boil that down? I mean, they're seeing that in the large. How do you boil that down into the small, into a programming model that's always there and you're always thinking about? We have some ideas, but that's an interesting question and a fascinating topic. But it breaks how we teach people. It breaks how we teach computer science and programming. And so we've got, how many generations is it going to take for them to figure this out? Or 20 years from now, they're all still going to be programming in a C-like syntax because they have to, and still be using IEEE floating point, thinking it's precise. Right? Your third one.
Yeah, and this has more to do with our yesterday's trip and the first part of your presentation. They were speaking about the boundaries. And when it comes to the notion of boundaries, there's a mathematical model what can happen at a boundary, and they either call it catastrophe theory or chaos theory. So when you were speaking about the ensembles, they behave okay in certain areas, and when it comes to boundaries, reality nature suddenly does something else because whatever.
There's a phase transition.
Yeah. How do these concepts apply to your ideas of ensembles, of computing models? How do you prevent from getting into these boundaries that suddenly a chaos happens or whatever?
Yeah. The way, that chart that I had about the ways that you harness emergence, one of those was feedback loops. If you look at, I think it was Wolfram, his Big Fat Cellular Automata book, right? He talks in there about these 3 domains of dynamics in cellular automata. You have the frozen domain where it's just locked, right? Nothing's changing. You have the chaotic domain where there's absolutely no patterns, and then you have the complex domain in the middle, the complex adaptive. You've heard of complex adaptive systems and complexity theory as opposed to chaos theory. And what you have to do, this is one of those things that we learned, while I was at KSC and later, and also in the work I've done in AI, is the way that you harness emergence, because the problem with emergence is easy. It's easy to make things emerge. Guess what? Bugs are emergent behavior. It's something you didn't expect, right? It's a behavior you didn't expect, and it emerges out of your code. So you get 1,000 things and you turn them all on each other, right? And guess what? They start doing weird stuff you don't understand. That's easy to do. The hard thing is how do you do this large-scale emergent phenomenon and steer it in a useful direction to do useful work? One of the secrets to that is adding lots and lots and lots of feedback loops. And an example, someone to go read on this is Stu Kaufman, who wrote some fascinating books on this as well. He was using NK models with, I won't go into it, it's too much to talk about. But the idea is that if you put feedback loops in the system that nudge, so you got this big chaotic mess of things going on, and there's all kinds of behaviors that are trying to lock in to the whole group, sort of like a flock. And what you have is you have these little things that just kind of keep nudging it in the right direction. You have lots and lots of those little feedback loops that just kind of push it in the right direction. Because you can't say explicitly, deterministically, how you want the system to behave. Because if you do that, you're not using emergence, right? You're just writing code. You're writing straight ahead declarative code. So if you turn that around and you say, you hedge it in with lots of feedback loops that nudge it in the right direction, you can steer emergence into the direction you want. And that's how you deal with those boundary conditions, is you put something on that boundary that nudges it back the other way. And the closer it gets, the stronger it nudges. And so you build effectively very much like a constraint system around it that keeps everything kind of in the space that you want, but still gives it the dynamics so it can be really adaptive and without you having to explicitly program the adaptivity. Other questions?
Talking about your gerunds and adverbs, maybe could you contrast with that with aspect-oriented programming? Would you see it as aspects as a generalization or sort of an orthogonal type of concept?
I really think it's orthogonal because that was a lot more about composition of capabilities.
Right. This
Right.
seems the same way. In a
Well,
sense.
this is not, but you see, we're talking about adverbs being kind of universally applicable to any message send. So, you know, whatever you're actually sending, now you're going to tell the ensemble with the adverb, you're going to say, how do I want you to do this, sort of? Not explicitly, but kind of at a high level. Now, you might be very explicit, like sequentially or concurrently, right? Those are the trivial ones. But you know, you can do things like first to finish. You know, where you say, as soon as anyone comes back with an answer, tell everyone else to stop. Right? There's no good adverb for this that we found, but that's an example of one.
Sure, whereas aspects are selectively specific, is that the contrast you're trying to say, is it generally, as opposed to generally specific?
Well, but you
Generally
don't
applicable?
use adverbs. I mean, you can compose adverbs, but when you compose adverbs, what you're doing is composing an execution strategy for a particular message send. Right? That says nothing about how I'm composing behavior in an object space. You know, where you talk about aspects, you're saying, well, this is this particular kind of behavior that it has, and I'm going to have that in several places. It seems to me kind of really orthogonal in space. I mean, I may not understand it well enough what you're referencing, but these are just talking about the behavior of really it's a clue to the VM about how you really want this work done. It's not saying anything about how the objects are designed, how their behavior is distributed. None of that's being dealt with at all.
I see how you're differentiating it. It seems like you could use them both interchangeably in some ways, but yeah.
You probably could. You probably could. We've got a few more hands.
Yes, you mentioned flocks. Have you considered lower level, that being bacteria? There's
Sure.
some interesting things as far as how they communicate.
Yeah, they communicate. You're talking about quorum sensing, and actually quorum sensing happens in lots of things, but quorum sensing in bacteria and in cellular biology. Right.
When they work, when they figure out, oh, there's enough of us, let's do this.
Yep, that's quorum sensing. And they do that by chemical concentrations in their local neighborhoods. And that is stigmergy. By the way, go look at them. I should have had a reference. There's a website, Evolution of Computing. I think it's .com. Evolution of Computing. It's written by Steve Burback, one of my longtime colleagues, and who, by the way, was one of the founders of SoftSmarts, did the first Smalltalk on the PC, and he was also the project manager or something like that for Apple Smalltalk way back in the beginning. But he has a whole website on this whole emergence thing and how to deal with emergence, emerging meta levels, and stigmergy is one of those things. It's sideband communication, basically. But it's very, very powerful. And it's that kind of thinking where you're not talking about sending a direct message, you're leaving a note and walking away and knowing that there's enough people coming by that someone's going to pick up the note and do what it says. You know, it's that kind of a thought. Others? In the back?
So I was just curious if you see any pushback from folks who are kind of advocates of the functional paradigm in terms of it, you know, evaluation of expressions with not in an imperative way, but how that kind of solves. I wouldn't personally want to think that way, but how that kind of solves a lot of this, multiple core, and since you don't, you don't have one thing happening after another. I just wondered if you had a lot of that in the community, people really advocating for that.
Yeah, our community is very, very small. So we're almost invisible. So we don't get a lot of pushback because very few people know what we're doing.
So have anybody on your team thought about that or talked about it?
Yeah, because in fact, Dave Ungar is a great guy to talk to about this because he has a great answer, and I forget what his great answer is. But I mean, even functional programming, I was talking about how everybody's taking some fairly radical ways of rethinking programming. Functional programming is an example of that. They started a little earlier, right? But I mean, it has a lot of problems as well. I mean, go ask your favorite functional programming guy what's the dirty little secrets about functional programming and see if he'll tell you, because it's got its own problems. It's not the panacea. There isn't a panacea yet. We haven't found one. That's what makes this very challenging. Any others? Yeah, Rob.
So I've got two things. One is about the adverbs and gerunds. I've heard sort of talk a couple times, and it sounds very intriguing. When you say these adverbs are just such an obvious meaning, they don't have an obvious meaning to me. I'm not sure exactly what you mean by them. Last time I looked, which was at least a year ago, looked on your website, I didn't see a paper that was defining them or
Just about that.
Is there something about that? Do you have something that
I don't think we
focuses
have
on-
I don't think we've done a paper
because
just on that yet.
I think that this is a case where you've been working on it for so long that it seems very natural. And there's a lot of cases
No, you're
where
exactly
I've
right.
seen something that they tell it to me the first time, and it's intriguing, but I don't really understand it. And then after I've been working with it for a few months, oh yes, it's so obvious. Everybody should, but it making that breakthrough, it always
You're exactly
it
right.
isn't quite as easy as you might say. So that I think that's something that I would like to. I'm intrigued by it. I would like to know more about it, but every time I hear it, it's just like right on the tip. And
I think where that's probably going to first come from is probably out of Andrew Black's group,
okay.
because they're kind of our collaborators. The Stefan and Theo and everybody in Belgium have been working primarily on the virtual machine side. Andrew and his folks have been working on adverbs and ensembles and language, model issues and stuff, and that's probably where the first papers are going to come from. But you're exactly right about that. That it's been in my head too long, right, for it to not seem natural. But it's true about any kind of language, right? This is natural language, so some of it is going to seem that way and some of it's not. And when you start, it's just like when you say display on. Well, what does that mean? Well, but we all know what it means because we're small talkers, right? It's kind of that thing. Yeah.
So the other thing is imprecision, and it's easy to criticize computer people that we see a formula, we expect there to be an answer to it, and yes, we definitely fall into this problem of expecting there to be a single answer, expecting you run a program, you get the right answer for the program. We write our tests, right? You write unit tests, give it this input, was the output this one particular thing?
Yeah.
This is actually, but we're not the only ones. This is a very generic problem people have. And looking at accounting, for example, accountants are exactly the same way. You do the end of the year report and we say, our company made this much profit. And the government has laws that say, you will say how much profit you made and you pay this much tax based upon this much profit. And yet, we don't, you look at these banks and they give you these financial statements and they claim that they're worth a certain amount of money because they own all these mortgages, and nobody knows what those mortgages are really worth. And some of these banks are probably, some of the very biggest banks in the country might be worth negative amounts of money, and nobody knows. And yet they're not only giving out reports every year, people are getting bonuses based on the reports they gave out. We made so much money, and so I got my bonus of $1 million because of that. And this just happens everywhere. That everyone, we're expecting that we know just what we get, these very precise things, and and I think it's a sort of a delusion of our whole society.
Well, it's a
having.
delusion.
It's not, but it's definitely, we share that delusion. Okay, so it is something that we need to sort of break ourselves of as being too precise, when it isn't right. But it's actually one of the things that's hard is because our whole society has that delusion.
Yeah, and as engineers and especially computer people, we've been suffering under that delusion for a long time because we actually believe in ones and zeros, right? You get down in the chip, you go to a gate, guess what? There's no ones and zeros there. There's some sort of probability that there's enough of a charge on this one more than a threshold somewhere, right? And that's the whole basis of computing. So, simple binary logic and all that kind of stuff, and Boolean logic and math and all that kind of, it's all an illusion. It's been a very useful illusion. But what's interesting is technology is changing to the point now where we have to challenge the illusion if we're going to make progress and do new kinds of applications. So it's forcing us to revisit it. Any others? Yeah, Georg.
I wanted to come back to to the point of adverbs and gerundum.
Mm-hmm.
So if you use the word fast, do this, blah, 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 fast. Quickly.
There's almost always an ly word that you can use.
Yeah, okay. Then it's an adverb.
Yeah.
If you say, do this, running.
Running?
While you are running. So you use the word running instead of quickly. That's a gerundium. So that should express to you that I didn't see the difference between a gerundium and an adverb, because you can express almost the same thing this way or the other way. So do examples that we can
And then you have
understand.
things like, you have ing, ly words, right? I mean,
Runningly, yeah.
Natural language is really fuzzy and messy, right? And it overlaps all over the place. What we decided to do when we had the idea about adverbs, I went and looked at a bunch of them. I started categorizing them. I had a long list of them that I didn't want to put up that actually made a lot of sense. When you looked at it and you said, yeah, that's an idiom that I use in my programming. I just didn't have a name for it. Obviously, you can do some of the same things with natural language in whatever form. We just made the decision to say, there's so many ly words out there that will probably be one that expresses what you want. And it's a nice thing in English, I don't know what it is in other languages, but if you sit there and you say, I want you to do this way, and do this with the results. That's the pattern. That's the message sending pattern that we use. Here's the job I want you to do. I may have some parameters. Here's some hints, what am I trying to say? Some parameters around how I want you to do it. And here's what I want you to do with the results. So the results became the ing words. The parameters around the execution strategy became the ly words. And that's why we did it. And it seemed to work when you wrote the code. I wrote a bunch of virtual code that wasn't implemented just to kind of test it out. And it makes these really nice sentences that really kind of expresses a lot of intent. And that's what Ward always taught me, right? Intention revealing words is really important. And that's one of the reasons why we thought we were onto something. Yeah.
Just a remark to this. It seems to me, or at least the way I understand this, is that to oversimplify it a little bit, the adverb and gerund seems to me like the map and reduce part in map reduce. The adverb is the mapping, and the gerund would be then the reduce step, sort of.
It's an oversimplification because adverbs and gerunds are actually a huge superset over map and reduce. Map and reduce is an example.
Right.
And in fact, I didn't do it but it'd be a nice example to show. You take a typical MapReduce application, and then you turn it and write it, with ensembles and adverbs and gerunds, and what you'll see. And in fact, you can describe that whole process in one line of code with natural language instead of, here's all my map code. Now, we did say these things could have parameters, right? We found that we needed them. A lot of those parameters might be blocks. So how do you do this? We had one that was called neighborly, because we had all these Boyd's algorithms that they needed to find nearest neighbor. So this nearest neighbor thing. So I want you to do this, but I want you to do this in neighborhood clusters. Is kind of what neighborly meant. Well, how do I determine what the neighbor is? Because I don't know who's out there. So I need some sort of way of handing them some behavior that says, here's how I want you to find your neighbor. Because they may not understand the message neighbor or whatever. So I could hand them a block. They could do double dispatch. You do a lot of different things. But it does get more complicated when you start putting parameters on all your meta function stuff. Which is what these things are. But you end up explicitly saying what you're doing instead of it being implicit in a bunch of glue code. Yeah.
I just had also a question. The thing that I sort of struggle with a little bit is that how do you know when you are reasoning about an answer you got if it is correct or not, right? In our traditional scheme, it's correct because it came out of this formula, and we believe that the formula produces the right answer.
You just answered your own question. At the basis of it all is faith. You believe that you might have a buggy algorithm today.
Right, but you are also talking about the mechanism where you have processes in the background, and looking at the system and trying to find the ones that are out of whack.
Now that's not correcting. That's not proving truth. That's just consistency. That's something we can check. So like the example that I didn't go into that we're doing is in-memory cubing, which is an analytics tool. It's basically a high-dimensional spreadsheet, right? And they've got all these huge aggregation matrices, and everything's all kind of tied up. So the CEO of a company can watch his dashboard dance, and hundreds of people down below are changing little parts of this high-dimensional spreadsheet all the time. Now, if you think about that as a programming problem, it's a huge constraint network with these huge roll-up functions. And you literally cannot synchronize everything all the time. So what you'd have is the CEO's looking at a dashboard that needs this part of the huge tree of all this stuff, high dimensional tree, and over here some modifications being made that don't impact what he's seeing. So for right now, it's okay that it's not synced up. It does have to get there eventually. You know, that's what I mean by the consistency correctors. You know that the whole network is out of sync. You know that number, you know, is okay, but if he goes to the next page of his thing, it's going to be wrong. You know, because that's going to require this thread of calculation. And so you have a window in time when you can correct things. And sync things
so
up.
the notion of consistency is sort of something that will work automatically, or do you have to somehow express what it means to be consistent?
In that case, well, in that case you have to obviously express what it means to be consistent. What we did in that sense was we had this large constraint network that understands when it's not consistent, when things are out of sync. And the consistency corrector processes would run around and find those little pockets of inconsistency and fix them as it was going. Some really interesting results of that. That was actually in a recent paper, I think at DLS, on that shows some of the results of that research. Yeah.
One of the things that caught my attention in your talk was the notion of some of the processors having higher failure rates that are
soft errors, yeah.
Soft errors,
yeah.
And resulting in less precise, we're moving towards less precise. So I was wondering if in 50 years, if we figure this out and we have we've built systems which we've become very dependent on, but we start to have failures, if we will find ourselves sort of enslaved to computers, enslaved to the system we've become very dependent on by having to scramble around and...
Last time I looked, I already am.
Yeah, but even more because we won't be able to understand them as well because
we can't now.
But it's going. But
I
you're
know
saying
what
it's
you're
even.
saying.
What you said is that it's even going to be less understandable. We cannot comprehend the emergent phenomena that's going to happen, and we can't comprehend the side effects, all the things. It's going to get even worse because of what you said.
Well,
right?
what you do is you build in safeguards. I mean, think of flash crashes on the market, right? Flash crashes happen now pretty regularly. And we even know that they're going to happen. We know that they had happened, we analyze them, we know why they happened, and guess what? They still happen. Well, why? Because we've got a bazillion computers, you know, that are doing program trading all the time, and that's guess what? An emergent system that has boundaries, that goes into catastrophic failure, and that's what a flash crash is, right?
And then they put in a rule to help
to try to nudge it the other way or prevent. And
or
in that
cut
case,
it off,
the SEC does, right? The SEC says you can't do such and such kind of thing. But you can't explore that whole space ahead of time because it's too big a space. I don't know how many dimensions this is, but it's big. So what that means is as you go into the future, what you have to do is you have to put in these safeguards. You have to build systems with feedback loops. You have to instrument the heck out of them. And you have to do serious analytics on all that instrumented data at the same time of getting your kind of normal job done. That's why, of course, you know, when IBM starts talking about smarter planet and all the, you know, everything else, that's what we're talking about. That's the world we're headed towards.
Thanks.
Mm-hmm.
No, Chris, I think the real answer there is that's humanity. We already live in that. All right, who's going to be the next president of the United States? Yeah. You know.
Oh yeah, that was it.
So, you know, it'll just be more.
Great, and I need to talk after that. Awesome. So you were talking about how, well, you and others, were talking about how we should at least consider getting away from having precise answers. Mm-hmm. Well, one way or two of doing that is to ignore data. So why not? You know, I don't care. But if you ignore data, you make your problem smaller, and if it's smaller, then why did we need, you know, 1 million cores and exabytes?
Because the problems are really, really, really big, and you can lose a lot of data and still have a petabyte of data you got to sort through.
Can you give examples of that?
Yeah. So in Afghanistan, when you know, when they're going to have a convoy through the roads of Afghanistan, they have to worry about what? They have to worry about IEDs. Okay. Somewhere up there, people are listening because they can in wartime. They're listening to all the cell phone calls in all the languages and all the GPS signals and everything else, and they've got to figure out what's the likelihood that if these soldiers in a supply convoy take this road or that road in the next 30 seconds, they're more or less likely going to get blown up. That's terabytes of information per convoy per day. Okay? And yeah, it's all, and by the way, it's all uncertain, fuzzy, messy, error-prone, and even actively deceptive data. Actively deceptive data. Okay? So what you end up with, people actually are doing some interesting science on this in computer science. I left the charts out on the approximate computing side. Stanford and Microsoft, some guys from there did some research on automatically degrading the function of a web server. You know, it wasn't precise anymore, but they actually got a 14% improved power utilization and 20% more performance, and never hit the SLA, but like 1,000th of 1%, right? There's some guys at MIT that did a code perforation study. There's a paper on where inside the inner loop of a certain calculation, they would, based on a certain probability, just skip a few lines of code. The answers didn't change in any meaningful way, and they cut a whole bunch of performance out of the requirements. So there are ways of doing this. I'm not talking about just throwing up our hands and saying everything's fuzzy so we can't know anything anymore. It's just we do a lot of unnecessary precision, way unnecessary, because we just assumed we had to do it all the time. So there's lots of interesting stuff. There's a community of people that's starting up in this space. I think there's going to be a workshop maybe at UPSLO this year that Doug Kimmelman and Dave Unger are putting together on and it's, what is it? It's non-deterministic collections, where they're talking about, because there are some other researchers who are talking about non-determinism in just collection models, and our ensembles is kind of a case of that. And so there's actually going to be a workshop on that topic. So I mean, there's a lot of people that are kind of around the edges of this idea. It's sort of kind of in the air, but it's real early days still. Any other questions?
Yeah, I have one. So first of all, thanks for this talk. It was really, really enlightening. But I'm still a bit confused. So what are we really talking about? Like, aren't we trying to make computers behaving more like how we, the humans, are behaving? Like, have you tried to get inspiration from what is really happening, like not really at the level of a cell, but a group of cells that you might have like in the brain? Do you work with biologists? So what do you really get inspiration from?
Well, a lot of the ensembles and non-determinism stuff is there's a lot of biology and physiology examples that we were inspired by, right? So, and I have some background in some of that. And some of that's pretty common knowledge now. There have been a lot of fairly popularized science books on complexity theory and emergence and a lot of things like that over the last few years. But what you're talking about, if you start looking at especially human reasoning systems and the way they're structured, that's another one of my research areas is artificial general intelligence, and I've done a lot of work in that area. And what you have there, if you look at the models, albeit they're very poor, but artificial neural nets, various kinds of hidden Markov, kinds of approaches. What are you doing? You're producing, you're feeding it a bunch of examples, and it's producing a model, which, by the way, is a stochastic model, right? It's not precise. And when you feed it an answer, then if you fed it enough examples and it's a good enough model, then you get a classification out of it. That's very much a very uncertain kind of imprecise way of computing, but it's a very standard way of doing any kind of recognition tasks that we're doing now. When you start talking about human reasoning and stuff, you're talking about doing that kind of approach. The artificial neural net thing doesn't work. The reason it doesn't work for lots of reasons. Neural nets are great at classification. Lots of other things they're not very good at all that are human. But that's a whole nother talk. But the thing is, all of those situations, you talk about human behavior, it's all very fuzzy, it's all very imprecise, and it's all very dynamic and adaptive, and that's what makes us what we are. So yeah, can we get there? Makes for great research. I'm sure having a fun time doing it, but I don't know. We don't really understand it very well right now to be able to say what we'd do if we wanted to. Is that it?
It's actually time for lunch. And,
Good.
It was